Okay, this will be my second in my series about balancing chemical equations. And I'm going through this because I've developed this technique. Like I said, I'm sure I'm not the first one, but I just haven't seen anyone else do it before. Um, where I can take the problem of balancing a chemical equation and recast it in terms of solving a system of linear equations. So we can use the same techniques that we use for solving a system of linear equations with matrices and so on, if we so choose, to balance to the problem. We can apply it to balancing a chemical equation. Okay, so here I have a chemical equation I need to balance. I have four compounds, FeCl3, Be3PO4, twice, BeCl2, and FePO4. Okay, so here's a compound, here's a compound, here's a compound, and here's a compound. Now the problem in balancing a chemical equation is I need to find non-negative integers to multiply each compound, a different integer for each compound in general, so that the total number of like elements on each side of the equation are equal. In other words, we have the same number of ions on both sides, same number of chlorines on both sides, same number of oxygens on both sides, and so on. So this has to be true for balancing a chemical equation. So the way I do it using a linear algebra or system of linear equations approach is I think of each compound as representing a column vector. Okay, so this will be a column vector for my first compound here. This is a column vector for my second compound, column vector for my third compound, and column vector for my fourth compound. And then on each row, I'm going to have each row dedicated to every element, to each element that appears in the equation. And I just write these down in the order that the elements appear. So iron, we have an iron row, we have a chlorine row, we have here's a row for Be, here's a row for P, here's a row for O. Okay, this is the row for O, P, Be, Cl, and Fe. Now, as I said, I'm going to multiply this by a constant A, this by a constant B, and that has to equal C times this, constant C times that plus constant T. So the equation will look something like A times 1 plus B times 0 has to equal C times 0 plus D times 1. A times 3 plus B times 0 has to equal C times 2 plus D times 0, and so on. So this is sort of how I'm writing these equations, if you like. A and B and C and D are my constants. The green A, B, C, D are my column vectors. So this constant times this column vector plus this constant times this column vector has to equal this constant times this column vector and this constant times this column vector. Now that's not exactly what I have written here, because what I've done is I've taken everything on the right-hand side here and I've subtracted it from both sides of the equation. So the equation, the algebraic equation that I have developed from this balanced chemical equation problem is A times compound A plus B times compound B minus C times compound C minus D times compound D, and that has to equal 0. Okay, A times compound A plus B times compound B minus C times compound C minus D times compound D is equal to 0. So algebraically, I can write that as shown right here. Okay, here's my array matrix. Here's my constants that I need to solve for. So this is 1 times A plus 0 times B plus 0 times C minus 1 times D equals 0. This is 3 times A plus 0 times B minus 2 times C plus 0 times D equals 0. 0 times A plus 3 times B minus 1 times Z plus 0 times D equals 0, and so on. So first I write out my compounds in rows. Each row for each element that appears in the equation. I write out the number of atoms that appear in that compound for that element. So there are, for example, 3 chlorines here. And this then is my matrix. The only thing I do is I take all the elements over here, okay, and I subtract them from the elements on the left. So that gives me this equation. Here's where I subtract them. And this has to equal 0. Okay, so when I count up all of the atoms for all the elements on the left side, do that for each element, subtract the atoms for each element on the right side, the result must be there are no atoms left when I subtract the number of atoms on the right from the number of atoms on the left. So here is my linear algebra equation. Okay, now I just execute now a standard procedure for solving this type of linear algebra equation, for solving this set of this system of linear equations. So I do standard row operations to put this matrix here into what's called an upper diagonal form. And I represent the rows with these green numbers and circles. So this is row 1, this is row 2, this is row 3, row 4, row 5, and so on. So what I say is here, so I start the process of doing that. So first step I do here is I say, gee, let me take row 5, that's this row, and let me subtract from row 5 4 times the respective numbers in row 4. And when I do that, I'll put the answer in row 5. So what I'm doing is I'm taking 0, subtracting from it 4 times 0, which is still 0, and putting that answer in row 5. I'm taking 8, subtracting from that 4 times 2, which is 8, so 8 minus 8 is 0. I'm putting that in row 5. 4 times 0 subtracted from 0 is 0, and 4 times negative 1 is negative 4, and I subtract that from negative 4 and I get 0. So when I go through that process, I get all zeros on 5. And I go do a second set of row operations where I take row 2 and I subtract from it 3 times row 1 and put that back into row 2. So row 2 is 3. I subtract from that 3 times 1, so that gives me 0. 3 times 0, subtract from that, that's 0, subtract that from 0 is 0. 3 times 0 is 0, subtract that from negative 2, I still get a negative 2. And 3 times negative 1 is negative 3, and I subtract that from 0, and that gives me a positive 3. So after doing this second set of row operations, this is what I have in row 2. So this is now what my matrix looks like after performing those 2 sets of row operations on the matrix. Okay, I do another row operation. I do 2 times the row 3 and subtract from that 3 times row 4 and put that back into row 4. So, okay, 2 times row 3 is 0. I'm subtracting from that 0. I put that in row 4, so I still get 0 in row 4. 2 times row 3 is 0. I subtract that from, 2 times 3 is 6. I subtract that from, I subtract from that 3 times 2, which is 6. So when I put that back into row 4, I get a 0. So I get a 0 down here. Okay, 2 times negative 1 is negative 2. I subtract from that 3 times 0. That still gives me a negative 2 here. And then I have 2 times 0 is 0. I subtract from that 3 times a negative 1. And when I subtract and that gives me negative 3. When I subtract the negative 3, that gives me a positive 3. So this is now what my matrix looks like after doing that set of row operations. So I continue the process here. Okay, and here at the end, right here, okay, at this point, Actually, it looks like I don't continue the process. It looks like I'm pretty much done right there. So I have this this matrix equation. So 1 times A plus 0 times B plus 0 times C minus 1 times D is equal to 0. So that's A minus D equals 0. Okay, here I have 0, 0. I have negative 2 times C plus 3 times D equals 0. So that's this. Negative 2 times C plus 3 times D equals 0. And then over here, I have 3 times B minus 1 times C equals 0. So these now are the three simplified equations for my unknowns A, B, C, and D. And I need to solve these for integer values of A, B, C, and D. And as I've said before, I want to find the smallest non-negative integer values for A, B, C, and D. Now, here's how I go about doing it. So pay attention with this for a minute. I'm going to look at the coefficients multiplying each variable in each equation. So for example, in this, the coefficient here is 1. And the coefficient here, well, we could say it was 1 or negative 1 if we want to count that negative sign as part of the coefficient. But I'm only looking at the absolute value of the coefficients. So here it's 1, and here it's 1. So my two coefficients are 1. So what I want to do is I want to find the least common multiple of 1 and 1. That's pretty simple because the least common multiple is 1. In other words, what's the smallest number that when multiplied by an integer times 1 gives me 1? And what's the smallest number that when multiplied by an integer times 1 times this second one gives me 1? The answer is 1. So this is trivial. So here the least common multiple is 1 and 1. This one's a little bit more interesting. Okay, 2, the absolute value of 2 is 2. The absolute value of 3 is 3. So now I want to find the least common multiple of 2 and 3. That's 6. 6 is a number that is the least common multiple of 2 and 3. In other words, if I take the integer 3 and multiply it by 2, I get 6, and I take the integer 2 and multiply it by 3, and I get 6. It's only coincidence that 3 times 2 is 6, where this second number here is 3, and 2 times 3 is 6, where the first number here is 2. That's coincidence. If you don't know what least common multiple is, go look it up. Okay, what that means, as I tried looking it up, try looking at a Wikipedia. Okay, here I have my two coefficients. The absolute values are 3 and 1. So here I have 3 and 1. I want the least common multiple of 3 and 1 is 3. So these are the least common multiples for the coefficients of the variables, or the absolute values of the coefficients, for the three equations. So I look at the equation that has the largest least common multiple. That's this one. So I take that least common multiple, and then I divide that least common multiple by the coefficient, by 2, and then by 3. And this is going to tell me, if I take 6 and divide it by 2, it's going to tell me what the value of C needs to be. And if I take the value of 6 and divide it by 3, it tells me what the value of D needs to be. Okay? I haven't explained that. I'm just telling you how to do it for now. So I start with the largest least common multiple of 6, and I say, and that's for this equation, negative 2c plus 3d equals 0. So I take 6, divide it by the absolute value of this coefficient, that gives me 3. When I do that, that gives me the value of c for this term. Now I take 6 and divide it by the 3 here. When I do that, 6 divided by 3 is 2, and that gives me the value of d. So I now have the value of c is 3, and the value of d is 2. Well, with that, I can go back up to these equations. If the value of d is 2, then a must be 2, and the value of c is 3, then b must be 1. So I get a is 2 as b is 1 by going back and looking at the other equations. So that's pretty interesting here, how I do that. Now I could also, as I said, I think I can probably solve this by using a technique called integer programming. but don't really need to do that right now with these particular chemical equations. Okay, so that's another example of how I balance a chemical equation by recasting the problem as a system of linear equations. So let me just quickly review that here. Okay, go back up here. Okay, I use my compounds and I write my elemental rows like this. And I take everything that appears over here and I subtract that from the other side, from both sides of the equation, so that I can write my chemical balancing equation in the form of this matrix equation right here. And the problem is to solve for the constants A, B, C, and D. Okay, so I go through my elementary row operations to try to put this matrix as best as possible into upper diagonal form. And what I'm doing with that is I'm getting the simplest possible representation for this matrix here. And that gives me a set of relatively simple 3 equations. Notice this last equation for everything, where everything is 0, that doesn't contribute anything to the solution. Then I look for the least common multiple for the coefficients on the variables for each equation. I take the largest least common multiple and I solve for the unknown variables in that equation using that largest least common multiple. And I do it by taking the least common multiple and divide by 2 to give me the value of C. So 6 divided by 2 is 3. And I divide by 3 to give me value of D. That's 6 divided by 3 gives me D is equal to 2. So that gives me the values for C and D. Then I can go back and I plug them in to these other 2 equations to solve for A and B. Okay, so that's how I do that. And until my next example, happy balancing.